converging lenses, optical instruments like cameras, projectors, microscopes, binoculars, telescopes, etc., have drastically widened our view of the world. Eyeglasses allow millions of people to read and see in comfort. Have you ever wondered which optical component makes all this possible? It is simply a lens. A lens is a piece of a transparent material bound by two surfaces of which at least one is curved. A lens bound by two spherical surfaces, bulging outwards, is called a biconvex, or simply a convex lens. It is thicker in the middle than near the edges. A lens bound by two spherical surfaces, curved inwards, is called a biconcave, or simply a concave lens. It is thinner in the middle than at the edges. Let us understand certain terms related to these lenses. The central point of a lens is called its optical center. It is usually represented by the letter O. For these lenses, convex or concave, each surface forms a part of a sphere. The straight line passing through the optical center and the centers of these spheres is called the principal axis of the lens. Principal axis is perpendicular to the surfaces of the lens. The effective diameter of a spherical lens is called its aperture. It determines the amount of light that passes through the lens. Here, we shall confine our discussion to thin lenses whose aperture is much less than its radius of curvature. Let us understand the basics of refraction of light through a convex lens. A convex lens may be thought of as an arrangement of a number of portions of triangular prisms with a very small glass slab at the center. The base of each prism points towards the principal axis of the lens. We know that a ray of light incident on a prism bends towards its base and then emerges out. Now, let us see what happens when a beam of light parallel to the principal axis strikes the lens. We can see that these rays undergo refraction as they enter the lens and leave it. First, they bend towards the base of the respective prisms, and then emerge bending towards the principal axis. Thus, after refraction through the lens, they converge to a point on the principal axis on the other side of the lens. This point is called the focal point or principal focus of the lens and is usually denoted by F. Here, the refracted rays actually meet at the focus. Hence, a convex lens is said to have a real focus. Because a convex lens converges the light rays that are incident on it, it is called a converging lens. We can see that the bending of rays is maximum at the top and bottom prisms, and it reduces as we move towards the principal axis. This is because the top and bottom prisms have the greatest angle between the refracting surfaces. As we move towards the principal axis, this angle reduces. This causes corresponding decrease in bending of the rays. At the center, no bending occurs for the glass faces are parallel. The ray through the optical center emerges undeviated along its original direction. A single piece of glass that curves outward and converges the light incident on it is called a convex lens. The distance from the optical center to the focal point is called the focal length of the lens and is represented by F. According to the sign convention, the focal length of the convex lens is positive. Thicker lenses having greater curvature bend the light more and thus have shorter focal length. Hence, thicker convex lenses have more converging power. Let us see what happens if the parallel beams incident on the lens are inclined to the principal axis. After refraction through the convex lens, they converge to certain points in a plane containing the focal point. The plane passing through all such points, perpendicular to the principal axis, is called the focal plane of the lens. What if light rays parallel to the principal axis are incident on this lens from the other side? This lens has the same effect on light incident from the other side. Therefore, a convex lens has two focal points, usually represented by f1 and f2, one on each side, equidistant from the optical center. According to the principle of reversibility of light, a ray of light passing through the focal point of the convex lens emerges on the other side of the lens parallel to its principal axis. Having understood the action of convex lenses on various rays of light, let us now see how they form images. For different positions of the object, a convex lens forms images of varying sizes and nature at different locations. These lenses are therefore used in instruments like cameras, telescopes, etc., to form images that we see with our eye, which itself has a lens. Summary: a lens is a piece of a refracting medium bound by two surfaces, at least one of which is curved. A convex lens is thicker in the middle than at the edges. A lens may be thought of as an arrangement of a set of tiny prisms with a very small glass slab at the center. The focal point of a convex lens is the point on its principal axis where the light rays incident parallel to the axis converge after refraction through the lens. The distance from the optical center to the focal point is called the focal length, f, of the lens, and is positive for a convex lens. A convex lens is a converging lens and has two real foci. Lenses. Objectives: to understand the formation of a convex and a concave lens, and to understand how these lenses work. Convex lens. Arrange two prisms so that their rectangular rough surfaces are facing each other. The parallel rays incident on the prisms emerge on the other side after refraction and intersect at a point. Insert a few more slabs of rectangular prisms between the two prisms. The parallel rays incident on such an assembly will undergo maximum refraction at its top and bottom. The rays undergo no refraction at the center of the lens. Now, if we arrange two more prisms at the side of this arrangement, then the incident rays emerging from them also converge at the same point. A single piece of glass formed in this fashion is called a convex lens. We can consider these equally curved surfaces of the lens to be small parts of spheres. The center of these spheres is called the center of the curvature of the lens. The radius of the spheres is known as the radius of curvature of the lens. The line joining the center of curvature on both sides of the lens is known as the principal axis, which passes through the optical center of the lens. The light rays parallel to the principal axis and incident on one side of the lens undergo refraction and converge at a point on the principal axis on the other side. This point is called the focal point or focus of the lens. The distance from the optical center of the lens to the focal point is called the focal length of the lens. The focal length of the lens depends on its curvature. Take two lenses of the same diameter, but of different thickness and hence curvature. When the parallel light rays are incident on them, you can observe that the light rays passing through the thick lens undergo more refraction and get converged at a shorter distance, as compared to the thin lens, which causes less refraction. So we can observe that the thick lens has a shorter focal length than the thin lens. formed by the convex lens in this case is a real image of an object. The convex lens can focus the light from the sun to a point on the other side of the lens. The concentration of light energy at this point causes the paper to heat up and burn. The lens in a human eye is convex in nature. We should not look at the sun directly, as it can damage our eyes permanently. Hence, we have understood that the rays of light incident on a convex lens get converged on the other side. So it can also be called a converging lens. Let us look at another kind of lens, which diverges the light rays passing through it. Concave lens. Place two prisms with their vertices in contact and arrange a few slabs of rectangular prisms beside each of them. The parallel rays of light falling on such an arrangement refract away from the center. Overall, we can see that the light undergoes divergence and it emerges on the other side. A single piece of glass formed in this fashion, having inward curvature, is called a concave lens. The parallel rays of light incident on the concave lens undergo divergence as they emerge on the other side. If the divergent rays are extended backwards, then they appear to meet at one point on the principal axis on the same side of the object. This point is called the focal point of the concave lens. The sun viewed from a concave lens would appear as a point. If you place a paper at this point, it would not be heated. The image formed in this case is a virtual image. The concave lenses are used to correct short-sightedness in people suffering from myopia. A concave lens is also used in the peepholes of doors to get a minimized image of the person on the other side of the door. To summarize, we have understood that 1. Light rays parallel to the principal axis and incident on one side of the convex lens undergo refraction and converge at a point on the principal axis on the other side. 2. The focal length of thinner lens is greater than that of the thicker lens. 3. A real image produced by a convex lens is formed on the other side of the object. 4. The parallel rays of light incident on a concave lens undergo divergence as they emerge on the other side. And 5. The concave lens produces a virtual image that is an image formed on the same side of the object.
Hello students, Ms. Swanson here, and today we're going to look at how to draw ray diagrams of converging lenses. This picture here just shows the sort of diagram that we'll be drawing. So we have a couple learning goals today. You should be able to draw ray diagrams for converging lenses, and you should be able to describe images produced by converging lenses. So just like what we saw with the concave mirrors, there are a different set of rules depending on the location of the original object. So we have 5 different locations that we talk about, and we'll have different rules for several groupings of these. So one of the locations is beyond 2f prime, so that means further from the mirror than 2f prime, at 2f prime, between 2f prime and f prime, at f prime, and between f prime and the lens. So those are the 5 locations that we'll talk about. The first 3, so object beyond 2f prime, like in this picture here, at 2f prime or between f prime and 2f prime, those 3 all have the exact same rules. So we're going to group them together, and I'm just going to do one example that covers all 3. Now if you have an example in your worksheet that covers a different one, you'll still be using these exact same rules. So what we'll be doing, just like what you saw with the mirrors, it's really hard for me to draw on the tablet to get correct angles and have nice straight lines. So I'm going to be using an animation to show you what I would be drawing, and you'll follow along in your notes the drawing the way that the animation shows. So our first rule is that if we have an incident light ray that's parallel to the principal axis, and we're going to draw our arrowhead on there to show that it's moving towards the lens, so parallel to the principal axis, it will refract through the focus, so it will go through F. And again, we put another arrowhead on there to show that the light is moving in that direction through F. So that's our first rule. Our second rule is that if we have a light ray that's moving through the optical center, it will continue on in the exact same direction. So it won't refract, it'll just move through in a straight line. So those are our two rules that we'll be using for these three situations. Now, since we started drawing our light rays at the top of the balloon, that means where the light rays cross, which in this picture is between F and 2F, where they cross will also be the top of the balloon, because where the light rays started is the top, so where they cross will also be the top. So we can draw our picture like this. Now the string of the balloon went straight down to the principal axis, which means the string of the balloon of our image will go straight to the principal axis. Now it's upside down this time, but it will go straight to the principal axis. It doesn't go straight down, it moves towards the principal axis because the original object had the string moving towards the principal axis. So this is what our final image would look like. Now if we're describing it for the size, it's smaller. Attitude is inverted because they're facing in different directions. The location is between F and 2F, and the type is real. It's real because it's on the other side of the lens, and because lenses are transparent, light can actually move through the lens, so if it ends up on the opposite side of the lens from the original object, that is real. If it was on the same side, then that would be virtual because light doesn't bounce off of the lens and come back like it would with a mirror, so that would be a virtual image. If it's on the opposite side, then it will be a real image. So let's take, these characteristics vary depending on which of those three locations written at the top. Depending on which of those locations your object is at, you'll have slightly different characteristics here. These are the rules that I just explained. I'm not going to read through them, but if you'd like, you can pause the video and write them down for your notes. So let's take a look at the example when the object is at F prime. So in this case, our first rule will be that an incident light ray traveling parallel to the principal axis will refract through F. So this is the same as the first rule that we saw last time, and again drawing the arrowheads on there. The second rule, an incident parallel light ray traveling through the optical center will continue on in the same direction. So again, the same rule that we saw last time. What's different about this situation than the last one is that if we look at our refracted rays, they are parallel to each other, which means they will never cross. Now, we know where the top of the balloon will be based on where they cross, but if they never cross, that means there will never be an image. So if we look at the characteristics are that there is no image, so we can't describe it. Anytime the original object is located at F prime, there will never be an image. So this is always the case when it's at F prime. And here again are these are the descriptions of our light rays. I'm not going to read through them, but pause the video if you'd like to copy them into your notes. And then finally, let's see what happens when the object is between F prime and the lens. So our first light ray will be parallel to the principal axis, and it will refract through F. Our second will move through the optical center and continue on in a straight line. So again, the same two rules that we saw last time. The difference here is that if we look at our refracted rays, they're actually traveling away from each other. If they're traveling away from each other, they won't cross on that side of the lens. However, if we backtrack those refracted rays to the original first side of the lens, we'll see that they do cross. So if they're traveling away from each other, we need to back up those rays. So this is how it would look. The orange one traveling backwards to the original side of the lens, and same with the red line there. And now we can see that those two will cross on the other side of the lens, and where they cross, that's the tip of the balloon. So we'll draw the balloon. Again, with our original object, the string went straight down to the principal axis. So in our image, the string will go straight down to the principal axis, and we'll have an image that looks like this on the same side of the lens as the original object. So if we're describing this, it's larger. It is upright because they're both facing the same direction. it's beyond 2f prime, and this type is virtual because it's on the same side of the lens as the original object. And here are those rules if you'd like to copy them down in your notebook. So let's take another look at our learning goals. You should be able to draw ray diagrams for converging lenses, and you should be able to describe images produced by converging lenses. If you can do these things, fantastic. If not, please rewatch the video, and if you're still having trouble, come ask me in class tomorrow. Alright, that's all for now. Bye-bye.